We present potentially visible set generation with the disocclusion buffer. We introduce a caching architecture that replaces a conventional G buffer with a set of sparse tiles. The sparse tiles are organized in a layered image space. The tiles in the disocclusion buffer represent the scene geometry, but resampled into a sparse, regular grid in screen coordinates. Therefore, we can efficiently process the scene without using the original complex scene geometry. To build the buffer, we rasterize the scene from the current viewpoint. Object A spans 2 layers. It maps to 3 tiles in layer n-1 and 2 additional tiles in layer n. Objects B and C are both contained in layer n and overlap in the image. Therefore, the 2 objects jointly map to 2 tiles in layer n. Consider the scene with 4 objects. A rendering pipeline would combine all 4 objects into a single image. The 4 objects are located at different depths. The content of every layer is split into tiles. Tiles are a rectangular block of pixels. We pack the non-empty tiles into a tile buffer. Then we fill page table with pointers to the tiles in the tile buffer. The page table is indexed using the tile location in screen space and the layer number. Here, we see the layered structure of the cache, allowing us to compute the layer-based disocclusions. Now we can compute a potentially visible set. A potentially visible set must contain all tiles that are visible from any camera position within the view cell centered around the original viewpoint. We compute which tiles are disoccluded from layer 1. We show the corresponding region in orange. We also compute which tiles are disoccluded from layer 2. We show the corresponding region in blue. Only tiles that are disoccluded by all previous layers are added to the potentially visible set. The tile A in layer 3 is disoccluded by layer 2, but not disoccluded by layer 1. It is therefore not added to the potentially visible set. The tile B in layer 3 is disoccluded by both layer 1 and layer 2. It is therefore added to the potentially visible set. We compute all disocclusions from all layers in parallel without any need for synchronization. Finally, disocclusions are gathered for each tile in parallel to determine inclusion in the potentially visible set. High parallelism and order independence make our method about 1 order of magnitude faster than previous potentially visible set methods. Next, we show some examples from the scenes used in our evaluation. Primitives included in the potentially visible set are colored orange. Primitives not included in the potentially visible set are colored blue. We start with the Viking village scene. Second, we show the bistro exterior scene. Third, we show the big city scene.